This is one of those interesting simple things that very easily portray the complexity of nature, a pendulum. If the motion of a pendulum is traced through a circle with radius equal to maximum arc length that it swings in one side of the vertical line, then the arc length that it has traversed at a particular instance will be equal to its projection on the vertical diameter of the circle. This explanation is a direct result of the solution that we obtain after using Newton's second law to a system of pendulum and solving a second-order differential equation. One thing to note, however, is that the pendulum traces a sinusoidal path only when an approximation is made, that is, sin theta approximates theta for very small values of theta. And for that approximation, one time period of the pendulum is independent of the amplitude or theta max of the pendulum. But then, I wonder if you've given some of your thoughts over how would a pendulum with large angles behave in our frame of equations. Particularly, you not get to approximate sin theta with just theta, and consequently, you not get to reach the equation of pendulum's motion being represented by a circular function, that is a sin omega t. The time period of the pendulum then would also not be independent to the amplitude of the pendulum. For those curious minds who always take everything with a grain of salt, I have posted a link in the description of this video that will show how if you proceed without the approximation, you'd find that the time period would be equal to the given integral in the screen. And also that the motion of the pendulum would be instead dependent upon elliptical functions, on which, of course, I'll make a video after I understand them. Well, for what I'm trying to do in this video, we need not worry about elliptical functions at all. Turns out, for a large number of cases without updated time period, circular functions can also reasonably approximate the elliptical functions to represent motion of a large angle pendulum. So with time period and equations of motion set up for both small and large angle pendulums, we're gonna see how accurately small angle pendulum approximation works with increasing values of theta. In a few moments, I'm gonna play a simulation of pendulums to make clear my point of this video. For each case of theta max, also two pairs of different pendulums, each representing two different formulas. One representing a pendulum with small angle approximation, while other without it. As I start the simulation, note how as theta max increases, our formula for motion of pendulum predicted by small angle approximation falls miserably into pieces. But then it works pretty well for small angles. In fact, for large angles, our approximation predicts that the time period of the pendulum is way less than that is actually calculated by our integral friend that gives exact time period. So everyone, be ready for an exhilarating experience. I hope that you will enjoy it. Wasn't that beautiful? I don't know about you, but I found it somehow satisfyingly beautiful. How mathematics allows you to make approximations to model a system and build on that succinctly up to a certain degree. That's it for today. Thanks for watching. Like, share, subscribe, and help the channel grow.